In this example, we're going to take a look at how cocaine produces its characteristic high and then crashes once its effects wear off. The neurotransmitter that we are dealing with here is dopamine. Dopamine is released in the reward centers of the brain and increases our feelings of pleasure. And when dopamine binds to its receptors on the postsynaptic neuron, it opens ligand-gated sodium channels, allowing sodium to enter the postsynaptic neuron, thereby causing depolarization of the postsynaptic neuron. And so the postsynaptic neuron is excited. In effect, an EPSP is formed in the postsynaptic neuron. Once dopamine has finished its job, however, it must be returned to its synaptic vesicle. This is done by the dopamine reuptake transporters or dopamine reuptake receptors that are present in the presynaptic neuron. In this way, dopamine is returned to the synaptic vesicle, and so the levels of dopamine are not too high in the synaptic cleft. So this is where cocaine comes in. Cocaine blocks the dopamine reuptake receptor, thereby blocking the return of dopamine to its synaptic vesicles. So the levels of dopamine increase greatly in the synaptic cleft, thereby producing a very high level of pleasure, which is your characteristic high from cocaine. So what happens when cocaine levels go down? When the effect of cocaine wears off, these dopamine reuptake transporters open suddenly, and a great rush of dopamine goes back into the synaptic vesicles. As a result, the levels of dopamine is extremely low in the synaptic cleft, thereby causing the crash, which is characteristic after the effect of cocaine has worn off. Here's an example of how Prozac, a popular drug that is used to treat clinical depression, works. The neurotransmitter that we are dealing with here is serotonin. Serotonin increases feelings of contentment. When serotonin binds to its receptors on the postsynaptic neuron, it opens ligand-gated sodium channels. Sodium rushes in, causing depolarization of the postsynaptic neuron, thereby causing an EPSP. Once serotonin has finished its job, it is returned to its synaptic vesicles via serotonin reuptake receptors. They are very similar to the ones we saw for dopamine. These are present in the presynaptic neuron, so that levels of serotonin may not increase too much in the synaptic cleft. Here comes Prozac. When Prozac is prescribed, it blocks the serotonin reuptake receptors, or not all of them, but some of them. As a result, the levels of serotonin gradually increase and serotonin accumulates in the synaptic cleft. As a result, there is an elevation of mood and feelings of contentment. Here's an example of an IPSP, which is inhibitory postsynaptic potential. The neurotransmitter that is involved here is called GABA. GABA stands for gamma aminobutyric acid. The receptors for GABA are present on the postsynaptic neuron, and these receptors are ligand-gated chloride channels. Chloride is negatively charged, so when these channels open, chloride will rush in. In order to do that, the GABA must first bind to its receptor. GABA is shown in pink, and it binds to its blue receptor, and this causes the chloride channels to open, and chloride rushes in. Chloride brings with it negative charges, and this causes the membrane potential to go below the resting membrane potential and therefore cause a hyperpolarization of the postsynaptic neuron. Because of the hyperpolarization, it actually inhibits the neuron, and so we call this an inhibitory postsynaptic potential. Neurons that produce GABA are abundant in areas of the brain that deal with emotions. This part of the brain is called the limbic system. This makes sense because GABA causes the postsynaptic neurons to be inhibited, and this is very useful to keep emotions in check. People often drink alcohol to minimize the intensity of negative emotions that they experience and to promote relaxation. Alcohol brings about these effects by binding to GABA receptors on the postsynaptic neuron. Alcohol is shown in orange, binding to the blue GABA receptors. When it does that, it causes GABA, which is shown in pink, to bind more tightly to its receptor. It also causes the chloride channels, which are the GABA receptors, to open wider and to stay open for a longer period of time. As a result, more chloride enters the postsynaptic neuron via the GABA receptors, and this continues for a longer period of time. Since the chloride brings in negative charges into the postsynaptic neuron, it causes a prolonged hyperpolarization. We also have a prolonged IPSP, and so the effect of alcohol is much more pronounced on the limbic system than GABA alone. It is widely known that marijuana elevates the mood and promotes relaxation. So let's take a look at how marijuana acts on the brain and on the synapse in particular. So here we have a synapse. The action potential has just arrived at the synaptic knob. It opens voltage-gated calcium channels, which are in the synaptic knob. Calcium rushes in and causes exocytosis of the synaptic vesicles. These synaptic vesicles are carrying a neurotransmitter called glutamate. Glutamate is the most important excitatory neurotransmitter. So glutamate binds to its receptors on the postsynaptic neuron and opens ligand-gated sodium channels. Sodium rushes in and causes depolarization of the postsynaptic neuron. This is an EPSP. Glutamate tends to be highly excitatory to the point of being toxic. In order to counter the effect of glutamate, postsynaptic neurons often produce another neurotransmitter called Anandamide that is shown in blue. The word Ananda in Sanskrit means joy or bliss. So Anandamide leaves the postsynaptic neuron, goes to the presynaptic neuron, and binds to receptors called cannabinoid receptors, or CB1 receptor for short. That's shown in green. So the anandamide binds to that, and as a result, it causes the calcium channels to be blocked. So when the calcium channels are blocked, when the action potential arrives at the synaptic knob, the calcium channels are no longer functional as a result of this binding of anandamide. So no glutamate is released, no more glutamate is released into the synaptic cleft, and so the excitation of the postsynaptic neuron reduces quite a bit. So this is actually beneficial because we don't want the postsynaptic neurons to be in a very high level of excitation. This results in a roundabout way, results in elevating the mood and increasing relaxation. So what happens when someone uses marijuana? Marijuana contains a compound called tetrahydrocannabinol, which is THC for short. THC binds to CB1 receptors, but its effect is much more potent than the natural binding of anandamide, and so it lifts the mood much more and causes a profound level of relaxation. While the occasional use of marijuana can improve mood and promote relaxation, chronic use of marijuana can have adverse effects on memory and cognition. This is because majority of the CB1 receptors are present in the learning part of the brain, which is called the hippocampus. And when marijuana is abused on a regular basis, the THC binds to these receptors and lowers the level of cognition. This makes sense because glutamate, the neurotransmitter glutamate, has a direct role to play in long term memory and learning. And all of this is affected by the use of THC on a regular basis.